Hello again, my name is Nicholas Perryman, and this is my presentation for test two. So my problem this time around was the summation going from 0 to n of -1 to the k times k squared. And the instructions were to use the repertoire method to solve it or prove it. So the repertoire that I had going into this was for n terms, n squared terms, and n cubed terms. And we needed the n cubed terms because when you get the closed form, that gets you an n squared term. So that's why we go up to n cubed. So attempting the repertoire method, I converted the given summation into a recursive equation. So basically, the current n equals the previous n value plus whatever happens when you plug in the current n value. And then I tried the repertoire method in the form where it's -1 to the n, and that's multiplying alpha a to the n plus beta b to the n, not to the n, but bn. And um, gamma c n, and then also the n-1 terms. And this is where I got stuck because I didn't have a repertoire for -1 to the n terms. And when you're doing the repertoire method, you kind of need to pull out all of those n-1 terms, which you'll get the an-1 term when you just plug in an. So you can work from there. But the -1 to n-1, I didn't actually have a source for that term, so I couldn't pull it out of the equation somehow. And it was at this point that I was told that I could use any method to prove the summation. So this is where we get into the proof by induction. So starting the proof by induction, I first got the summation into, I guess, just like a plug and play equation, just using some formulas. So our original summation was equal to -1 to the n times n times n plus 1, and all of that over 2. So from there, I did the first step of proof by induction, which is checking the base case. So plug in for n 0, and on both sides you get 0. So then I just keep moving on with proof by induction. And so the next step is assuming that basically the summation equals that other equation, swapped out the n's for x's. I can set a final goal, which, if we can get to that, that will prove the summation. So in order to find that and prove that, I took the x plus 1 summation and I took off the x plus 1 term. So then I just had the x summation plus -1 to the x plus 1 and x plus 1 squared. So from there, I could plug in what we assumed about the basic x summation and then just kind of keep solving from there. After plugging that in, I foiled out the square, I took the -1 x plus 1 and separated one of the negative ones. And then I had to put it all over 2 so that everything was over the same uh, denominator. That also means that I multiplied the top of that part by 2. So from there, just combine everything and we can pull out our um, common multipliers, which is just the -1 to the x. And then we can just steadily simplify it down. So we multiplied the -1 that was on its own into the foiled out squared term. And then we can subtract those, well, add those to our um, x summation, the x summation equation. And so that cancels some things out. So we wind up with -1 to the x times -x squared minus 3x minus 2, all of that over 2. And since the x squared and 3x and 2 were all negative, we can pull out that -1. And then we can add it back to the other -1. Well, -1 to the x. So then we get the -1 to the x plus 1. We also factor out that polynomial term. So we get x plus 1 times x plus 2. And then just to make it match our original goal, we turn the x plus 2 into x plus 1 plus 1. And then everything matches. So it's proven with induction. And in conclusion, uh, obviously, I couldn't prove it with the repertoire method. I would like to figure out how to. So if you've got ideas or if you have some kind of explanation, I would absolutely love to hear that. And thanks for watching.